So this is a review of Chapter 11. So Chapter 11, we start to get into liquids, and then Chapter 12 is solids. And so since we talked about gases and the kinetic molecular theory of gases and how gases are free to move and they're not very attracted to each other, and that's what makes an ideal gas. And then we continued that discussion by saying what makes a gas less ideal is the fact that they are actually attracted to each other and do take up some space. Well, the main factor of why they're attracted to each other is covered in Chapter 11 when we start talking about intermolecular forces. So there are two main types of intermolecular forces that you need to be familiar with and be able to explain in detail. The first one is dispersion forces. So dispersion forces is where you have substances that are not polarized that are able to attract to each other. And the way they can do that is you have an atom that has its electron cloud, and that's going to come near another atom that also has its electron cloud. And as they approach each other, the electron clouds actually begin to interact with each other, right? The outermost part of the atom is the electrons, and so when the electrons approach each other, as the two atoms approach each other, those electrons are going to feel their repulsion for each other first. And so they start to push on each other. And so there's a force of repulsion coming between these two atoms. Well, when that happens, what can happen is sometimes some of the electrons will actually shift sides and get pushed away by the other electrons, and the atom itself then will change its shape. The electron cloud will get warped. And when the electron cloud gets warped, now you have a slight negative end and a slight positive end. And as that's forming, and this nucleus is becoming more exposed as the electrons are being pushed away, that positive is going to start attracting the electrons here towards it, and so you're going to start to have a warping of this atom as well, as more electrons start to move towards that size of the atom, and so we're going to end up with a slight negative and slight positive on that atom as well. And so in the process of doing that, we end up creating this force of attraction between the two atoms. And that's what we refer to as our induced dipole. It's not natural as far as the atom doesn't always have it, or the molecule doesn't always have it, but under these conditions where the electrons begin to repel each other, they can create this dipole, and so that's why it's induced. So this is what's going to happen when you have substances that are not polarized normally, but interact with other substances, and therefore they can create this temporary polarization. So this is only temporary. It's going to go right back. The electron's going to go back. We know this is a higher energy state for the particles to have the electrons unbalanced around the nucleus. But it is a state that can form, and it is a state, therefore, that will cause these two things to attract to each other. And there are some situations where that attraction is large enough that you're going to start to have your substances become liquids or solids. So what are the situations where this induced dipole can be large enough for that to occur? Well, one thing is it's easier to induce dipoles when your electron cloud is larger. So the larger the atom is, the bigger the radius of the atom, the stronger dispersion forces they are going to have when they interact with each other. The greater the induced dipole, the stronger the dispersion forces, and that's going to be related to the size of the electron cloud. So bigger electron clouds, stronger dispersion forces, more likely to be a liquid. The other thing that can cause this interaction to create strong enough dispersion forces to have liquids or solids is if you have a very large molecule. The bigger the molecule is, it's not about its mass as much as it's about how many points on that molecule do you have the ability to induce dipoles. The more locations on the molecule that will interact with the molecule next to it, the more possible locations of dipole induction that can occur, and therefore you're going to create a stronger dispersion force because of all those regions of space that can interact. So bigger, longer molecules like carbon chains and organic molecules that have real long carbon chains surrounded by hydrogens, those are going to have really strong dispersion forces because there's so many hydrogens that can interact with hydrogens on the other molecule. And so the two molecules line up, and you get pretty strong dispersion forces throughout the whole molecule. Even though each individual attraction is kind of weak, the whole molecule lining up next to a molecule will make it strong. And that's why your longer hydrocarbons end up having higher boiling points, because they're going to attract more strongly, so they're more likely to be liquids. And eventually, if the carbon chain gets big enough, they're more likely to be solids. So the two things that you want to look for dispersion forces is how big is the molecule, so how many points do you have on the molecule to create dispersion forces. And the other thing that you want to look for is if you're dealing with individual atoms or an individual atom as part of the molecule and you're comparing two molecules, you want to look at the size of the atom. So for instance, if you have something like this, right, where you have sulfur and hydrogen, that is going to have greater dispersion forces than this will. Because the sulfur is bigger, it's going to create stronger dispersion forces, right? Now, if you want to know which one of these two is going to interact more strongly with itself and therefore be more likely to be a liquid, we're going to look here, because we know that the OH is very polarized, so this is a very strong polar molecule. So this one's going to be polar, this one's going to be nonpolar for the most part, and this one's going to have the stronger dispersion forces because that sulfur atom is bigger than the oxygen atom, right? So stronger dispersion forces, more polar. Those are the two differences between these two, right? But those are the only differences, right? The only difference between these two is the sulfur and the oxygen. So that's what we're looking for here to talk about intermolecular forces. So bigger electron cloud, stronger dispersion forces. Now, that's not to say this doesn't have dispersion forces. All substances create dispersion forces. Some weak, some strong, but every substance creates dispersion forces. Not every substance will be polar and create dipole-dipole attractions, but all substances create dispersion forces. So if they ask you a question of what two types of forces, intermolecular forces, do you expect to find in this molecule, the first one you're going to write down is always going to be dispersion forces. The second one will be dipole-dipole, or maybe in the extreme case, hydrogen bonding. All right, so there's dispersion forces. So what about dipole-dipole? Well, we know that oxygen is highly electronegative, so it's going to pull the electrons towards itself. So we know that there's going to be a pretty strong negative here and a pretty strong positive out here. So now we have a polar part of the molecule, which isn't too different. You should always recognize that OH is being polar because we know that water is polar. So any place on a molecule that has the OH like what water has is going to be polarized. So this is a permanent dipole because of the fact that the oxygen's electronegativity is so much higher than the hydrogen's electronegativity. So since we have this permanent dipole, then we have a situation where the molecule will always have these charged ends to it. And that enables them to interact with any other molecule that has charged ends. So these two things are going to interact very, very well. So methanol should be pretty soluble in water. Water is going to be pretty soluble or pretty attracted to itself. So that's why water is more likely to be a liquid. That's why water is going to attract and dissolve ionic substances so much, because it's got charged ends, so do ionic compounds. So this is our model for being polar, and therefore we're going to have dipole-dipole interaction. Why dipole-dipole interaction? Well, because this has two poles, so this is a dipole, right? 1, 2, 2 poles, dipole, and this one has two poles, 1, 2, dipole, right? So when these two interact with each other, it's going to be called dipole-dipole interaction. Two polar molecules, two dipoles, interact, dipole-dipole. All right, and the extreme case of dipole-dipole, this is typically stronger than that if it's a one-off sort of thing, right? One dispersion force is not going to be as strong as typically a dipole-dipole attraction. But obviously we know there are places where the dispersion forces will win. but we also have more strong dipoles as our atoms become more and more polarized, as our electronegativities of our elements become higher and higher, especially bonding with hydrogen. We're going to get that extreme polarization. So anytime you have oxygen, nitrogen, or fluorine that's pulling the electrons away from a hydrogen, you're going to create a situation where you can form a hydrogen bond, which is where the hydrogen that's polarized on one molecule can interact with one of those three elements that's polarized on the other molecule, or at least has that non-bonding pair of electrons out there, right? So oxygen having those two pairs of non-bonding electrons makes it even more negative on that side. So hydrogen bonds does not mean you've created a bond with hydrogen, first of all, and it doesn't happen every time a molecule has hydrogen. This will not hydrogen bond with the molecule next to it. The reason why? This sulfur-hydrogen bond is not polar enough to create the polarity necessary to create the strong hydrogen bond. And the CH, remember, is nonpolar altogether, so that doesn't do anything, right? It has to be one of these three elements with hydrogen polarizing the hydrogen, making it very positive, and then that hydrogen attracting to one of those three things on a different molecule. That's what the hydrogen bond is. So it would be right here in this case. Okay, those are the main types of intermolecular forces. You do have van der Waals forces, which is where the molecules can wrap around each other, but I wouldn't use that as an explanation ever unless you're dealing with a long carbon chain like an octane or something like that. That's an explanation. Now, the relationship between all of this then is stronger the intermolecular forces, the more energy it takes to separate them. The more energy it takes to separate them, the less likely you're going to be to have that change phase, right? So stronger intermolecular forces means you're more likely to have first a solid, then a liquid, and least likely to have a gas. So as the intermolecular forces are weaker, you're more likely to have a gas because that's ideal, that they don't attract to each other. But the stronger those intermolecular forces are, the more they're going to be likely to attach to each other, the more likely you are to have a liquid and a solid, and the more energy you have to put in to break that force of attraction and separate them from each other so that you have the possibility of forming a gas, or if you have a solid, forming a liquid. Okay, so the next part of the chapter then got into the energy of changing phase and phase diagrams and heating curves and all that stuff. All right, so the first thing is that you have, if you have a solid, we know that it takes a certain amount of energy, which we call the heat of fusion, to turn that into a liquid, and then takes a certain amount of energy called the heat of vaporization to turn that into a gas. And the heat of vaporization tends to be significantly larger than the heat of fusion. To go directly from a solid to a gas is sublimation. And the value of the delta H of sublimation is equal to the value of the heat of fusion and the heat of vaporization put together. So some element like iodine that would go directly from solid to gas, that means that if you were to calculate what the energy transition was to do that, you'd see that that energy transition to do that is equal to how much if you could turn it into a liquid and then how much to turn that liquid into a gas. Going the other way, it's still heat of vaporization, heat of fusion, except instead of melting and then boiling, you're going to condense and then freeze, or deposit is the reverse of this. Okay, so what does that look like if we were to take water and start to heat it? Well, what we find is if we take water, and we'll say 0 is here and 100 is here, as in our temperature in degrees Celsius, if we take water that's below 0 degrees Celsius and start to heat it, we know that water at that point is in its solid phase, right? So the energy required to heat it from whatever temperature we started at to 0 is going to be based on delta H equals mc delta T, where we would have to use the specific heat for ice in order to calculate this correctly. But when we reach zero, we know that that's where we reach our phase change, and that's an equilibrium situation, right? At our phase change point, we have some of our solid turning into a liquid and some of our liquid turning back into a solid. Now, this is time as we're adding energy, which means we're never going to let it reach equilibrium. But the other thing about it reaching a phase change point is that the energy is going into not making the molecules move faster, but causing the molecules to separate from each other and be allowed to move more freely, right? It's more entropic, not enthalpic, right? So here, this is all talking about, since you have a change in temperature, this is talking about the change in their amount of movement, how fast they're moving. But when you reach zero, you're no longer talking about how fast they're moving, you're talking about how they're starting to separate from each other. So this is where the delta H equals the heat of fusion times the mass comes in, right? So you would just take this value and multiply it by whatever mass you have, and that's how much energy it's going to take to completely melt our substance. Once it's completely melted, then the temperature is free to change again, and then we're going to do MC delta T again. Now we're going to use the specific heat of water, and now that energy is going into making our particles move faster because we're having a temperature change again. When we reach the boiling point, though, again, we're overcoming those intermolecular forces. We're separating the particles from each other. We're giving them complete freedom of motion. And so this is where our delta H of vaporization comes in, times the mass is equal to our delta H. And then once it completely vaporizes, then you could do MC delta T again, because now you are adding that energy and it's allowing the gas to move faster and much more rapidly. So here's where our phase changes are happening. Here's where our intermolecular forces are occurring. Here, the intermolecular force is being overcome enough to allow movement. Allow movement and randomization. Up here, though, our intermolecular force is completely being overcome. So we're not going to have any more attraction to hold them together. So this is complete freedom of motion once you are vaporizing it. Okay, if we were to go the other way, obviously it would be the same in reverse for the condensation and the freezing, but it's still the same idea. Okay, and there's a very simple way that you can calculate those values to get through there. All right, so what else is important about liquids? Well, once you have liquids being formed, now you start to talk about vapor pressure, and you start to talk about how that's going to cause the liquid to behave. So we know our intermolecular forces, if they're strong, are going to hold our particles together pretty strongly. If that's the case, it's going to make them harder to flow. So the harder it is to flow, the less viscous it is. The ability to flow is called viscosity. So the more strongly it's attracted, the less it's going to flow, like maple syrup must be pretty strongly attracted, where other substances that aren't very attracted are going to flow very, very easily. So viscosity is one of the things. Surface tension is another thing that we get from strong intermolecular forces, where the particles on the surface are all so attracted to each other that they actually are pulled down and inward, and they increase the density at the top of the liquid because everything that would want to flow out is actually being pulled down and inward, so it makes that little dome at the top of your cup of water or whatever if you try to overfill it, right? So that surface tension, then that energy now, the density's higher, and all that energy's in there, and it's not being pulled in any other direction upward, let's say, in order to balance the energy. So you have to put extra energy in to break through that. And that energy that you have to put in to increase the volume of it and lower the density of it is the value for the surface tension. And we know we can float things on that. Stronger intermolecular forces, again, the big one that you want to know is that stronger intermolecular forces, the harder it's going to be to melt and boil, right? Stronger intermolecular forces, higher boiling points. Weaker intermolecular forces, lower boiling points. So what's the explanation for that? Well, the explanation for that comes down to vapor pressure. All right, your vapor pressure is a measure of the internal pressure, we'll say, of our liquid. All right, the molecules inside are exerting a pressure on each other, and if they want to create a gas, let's say, they're going to put that pressure on each other to try to create their own space. But if they don't quite have enough force to push the molecules away from each other to create that space, then you won't actually be able to form a gas in your liquid. So what is it that's determining how much force that's going to be? Well, what's going to determine how much force it's going to be is you have to recognize that if I want to make a bubble in here, the gas has a significantly lower density than the liquid does, which means the volume of space that the gas is going to occupy is going to be significantly larger than what it would occupy as a liquid. So if that's the case, if you're going to form a bubble in here, it means that the volume of the liquid actually has to go up, which doesn't seem like it's a big deal, except for the fact that we know there's particles above that are pushing down on that pretty strongly, right? You have your air pressure here. So as the pressure inside this bubble is being created by the liquid, it's battling against air pressure. So if the pressure inside this bubble is less than the air pressure pushing down, the bubble won't be able to form. It won't be able to expand its volume. It's going to get crushed and it's going to stay in the liquid phase. But if the pressure inside this bubble is equal to atmospheric pressure or even greater than it, then the bubble will be able to form and will be able to work its way out of the liquid and escape as a gas. And that's what we call boiling. So what makes this vapor pressure in here go up? Well, what will make it go up is making the particles move faster, collide more strongly, collide more frequently, which means that in order to increase the vapor pressure, you're going to increase the temperature. So your definition for boiling point is when you have raised the temperature of your liquid high enough that the vapor pressure inside the liquid is equal to or greater than the atmospheric pressure. Once you've heated this enough that the pressure inside this bubble, which is the vapor pressure, is higher than the atmospheric pressure or equal to it, the bubble can form, it can escape, and now we say it's boiled. And what's in that bubble? Whatever the liquid is in here, right? If there's no air getting into your pot of water, when you see bubbles in there, that's bubbles of water vapor, okay? College Board likes to ask that because so many people have a misconception on that. The bubble is water because the liquid is water. But anyway, so you got to get to the vapor pressure equal or greater than atmospheric pressure in order to get it to boil, which is why if you lower the pressure up here, right, if you can take away some of the atmospheric pressure, this bubble will form more easily and therefore you'll boil at a lower temperature. If you increase the pressure on the surface of it, then it's going to be harder for this bubble to form, so you're going to have to put more energy in to do that, and that raises the boiling point. And that's why the less pressure you have, the easier it is to boil water, and that's why we can boil water at room temperature, and it's not really hot as far as we're concerned. Too many people also have that misconception that things have to be hot to boil. That's a weak idea because if you think about it, oxygen's already boiled. And when you see liquid oxygen, it is really, really cold. So things don't have to be hot to boil. They just have to reach the point where the pressure in here is greater than that. Now, some things are going to do this easier. Things that have weaker intermolecular forces will form this bubble at a higher pressure much quicker. If things tend to evaporate rapidly, that gas bubble is going to form very, very easily. So weaker intermolecular forces are going to have higher vapor pressures. They're more likely to evaporate. They're more likely to create a gas. They're more likely to escape from each other. So they're going to boil at lower temperatures. But something like water that has a really strong intermolecular force is going to have a harder time forming this bubble because it's so attracted to itself. And so you're going to have to put a lot more energy into it before you get the vapor pressure high enough to form this bubble and break out of the solution. So that's the definition for boiling. Understand the pressure component of that. All right, and the last part is where we talk about the phase diagrams. We're looking at pressure and volume, and then we have our vapor pressure curve. All right, that's where our vapor pressure is. And in here, we're going to have solid, liquid, and gas. We know this is water because that's going up to the left. If it was another substance that wasn't water, it would go up to the right. It has to do with the density of water being lower as a solid than a liquid, and that's what makes this go up to the left. But regardless, here we have a point that we call the triple point, and that's where we would be at equilibrium under those pressure and, whoops, did I put volume here? What am I doing? Temperature. When we are at the certain pressure and temperature point, we will have a situation where all three phases will be able to be in equilibrium with each other, right? And that's what the triple point is right there. The rest of these, any point on here, pressure and temperature-wise, it's going to tell you these lines, and the vapor pressure is where you would be at equilibrium between solid and liquid if you're in here, and liquid and gas if you're in here. Now, the energy doesn't change. The heat of vaporization, the heat of fusion doesn't change, but the conditions that you're doing it under is changing, and that's what makes it easier to be a solid, a liquid, or a gas at certain points. So you reach a point where they call it the critical point, where when you go beyond that, you really don't have a true liquid or gas anymore. The temperature's high enough that your liquid should have boiled, and so it moves freely like a gas does, but your pressure's high enough that it doesn't allow the gas to expand rapidly, so it has the density of a liquid, but the freedom of motion of a gas, and that's what we consider to be a supercritical fluid or supercritical state. And so this is called the critical point because it's the last time that we can actually define what the phase is in, whether it's a liquid or a solid or a gas. That's not something that's going to be that important. In fact, this diagram is something that College Board says that they won't make you draw pictures of or ask you directly about, except they're going to ask you that concept. And so you should understand what the idea of the triple point is. You should understand what that vapor pressure curve is all about. It's all about forming this bubble and whether or not you can. And then the last thing is how you can modify this. Well, when we make solutions, this curve changes a little bit because then it lowers the vapor pressure curve. So when we get to chapter 13, I'll discuss that. So I guess the last thing I just want to address about the phase diagram is that if you have a pressure, like atmospheric pressure, so for water it might be up here somewhere, and you draw a line straight across as one atmosphere, then where it crosses these two lines are the temperatures of your melting point and your boiling point. So it makes it real convenient to find that. If this was lower than the triple point, then that means you're going from solid to gas. So that would be your sublimation and depositing, where you're not ever going to see the liquid phase. So carbon dioxide would be down there, right? And they like to ask carbon dioxide a lot because you get so much from carbon dioxide. You can talk about the fact that it never forms a liquid. You can do all sorts of reactions with it. It is the gas that they always want to target about. When you put it in water, it makes an acid solution. So they like to ask a lot of questions about carbon dioxide. So keep that in mind when they're coming up with these questions. Carbon dioxide is a big deal. So understand that carbon dioxide would be down below the triple point. So you're going to go directly from solid to gas. So that concludes everything in chapter 11. We're going to do chapter 12. That will be a short one. And then we'll get into solutions.